gave it to me.
Okay,
Here it is.
there we go. We get this stuff eventually.
Okay,
So we missed the great introduction of Logan, but he's from the National Weather Service, correct?
That is correct. Yep.
And do whatever introduction you want. We missed the formal introduction off the recording, but I'll assure everyone who's watching the recording it was quite glowing. Logan, feel free to introduce yourself and go right ahead.
All right. Well, much appreciated, Steve. Well, hello, everybody. Good morning. Thanks for joining me today. And I apologize for the last meeting that we tried to do that it didn't end up working out because I had to cover for some severe weather that we got in December. So meteorology always kind of keeps you on edge. And that's one of the things I do love about this field and this job, that there's never really a dull day. But for those that don't know, so yeah, my name is Logan and I am a meteorologist at the National Weather Service office in Wilmington. So I've been here actually only about a year and a half now. So I graduated from Ohio University in 2018 for my undergrad, and then 2020 I did my master's. So my undergrad was in meteorology and my master's was geography, but with a focus in sort of like atmospheric sciences. And I did a little bit of other things too with working like GIS and programming and different things like that too, to just kind of increase my vocabulary in different fields in the physical geography realm. So I will go ahead and share my screen here. Let's see. Oh, let's see it. It says host disabled participant screen sharing.
And Gary walked away and Sue's camera's off. Sue, are you there?
Yeah, I'm here. Let me,
To make you co-host? Yeah, so I think you can give him presenting. For the couple of new folks we have, just FYI, this was a rougher entry to the meeting than we usually have. We've been a little bumpy this morning. That's okay. It happens.
All right, it's a Saturday.
It does happen. I know I need a second cup of coffee myself, so. And technology, love it, but it can hate it too.
Absolutely.
I don't see that option.
Gary, we're trying to give Logan presenting ability. Can you?
oh, okay, let's see. Oh, 1 second. Okay, Logan. Stop video. I don't see a category for that. Do you guys see it? Record.
Are you saying he doesn't have permissions for the
Allow
share
to-
screen?
We're trying to find where
Correct.
they
Oh,
are.
share screen?
Yeah.
Oh, sorry. All right. All right. Does that work?
Try it. What did it call? Yep.
Okay,
Good.
great.
Very good.
Awesome.
Sorry.
Thanks so much, guys.
I
Oh,
forgot
no
about
worries.
that. Yeah.
No worries. It's always little nuances that you have to
Yeah.
remember when setting up a call, and it's impossible to do. So
Sue, did you try to share screen for him?
I could not
We-
find it.
Okay,
We
talk
got it
about it
going now.
later.
Let's not worry about
okay,
it.
okay.
Yeah, that's
Go
working.
ahead, Logan.
no worries, guys. I got nowhere to be today. So, well, again, thank you so much for having me. I'm looking forward to talking to you guys a little bit today about meteorology and specifically about the National Weather Service and what it is that we do. So just to kind of give a quick overview of my presentation, I'll kind of talk a little bit about the history of the National Weather Service and sort of how it came to be, just really briefly. And then we'll talk a little bit more about the science. So some of the things that we do at the Weather Service, the observations we collect, the tools that we use to forecast day-to-day things, and then talk a little bit about the challenges too of forecasting in the Ohio Valley. So first and foremost, so you'll notice a timeline down at the bottom of your screen there. So I won't go over every single point, but you can kind of use those as a reference and kind of, quickly glance over some of the different highlights that we've seen. So we're going to jump back all the way toward the 1870s. So in this era, we actually have our first official weather report that was given by the US government. So the first official weather report was actually given by this guy named Cleveland Abbey. And Cleveland Abbey was kind of known as the founder of the modern day National Weather Service, because he was the one that kind of initiated, the program for collecting different routine meteorological variables. And the cool thing about where he took these observations was that they were from a local area here in Cincinnati at Pike's Opera House. So what Cleveland Abbey did is he basically took took four main meteorological elements when he was doing these observations. So the first of them was weather, basically just the present weather type. So saying whether it's sunny outside or raining or snowing. The second was temperature. The third was wind direction. And the fourth was the barometric pressure. So we'll jump ahead now to the 1910s, where in 1915, the US Weather Bureau actually built a weather observatory on Lafayette Circle. And actually, the cool thing about this place was that the weather instruments were located on the roof of this building. And the chief meteorologist would actually live in this house as well. So back in the 1910s, they were teleworking a lot as well, I guess. But the ownership of the building was eventually transferred from the Weather Bureau to the University of Cincinnati in about 1965. And today it actually just serves as a private residence. So jumping ahead now. So before I talk about this, the Weather Bureau actually created offices here in the 1930s at Dayton, Columbus, and then eventually Cincinnati. So those three offices were they were called Weather Service offices. And so they were kind of like these smaller offices. They only I think they only held maybe about 5 people or something that worked there. It was a pretty small group of people that would work at these offices, but they had them located in sort of the 3 big metropolitan areas throughout kind of South Central Ohio. So in the early 1990s, the National Weather Service actually then went under a massive reorganization effort where they consolidated a lot of these WSOs into what are called weather forecast offices now. And so the WFO is kind of the terminology that we use to just describe a typical National Weather Service office. So what they did is they consolidated people that were in Cincinnati, Columbus, and Dayton, and decided to try to pick some middle ground point, and that happened to be Wilmington, Ohio. So by the mid-1990s, you can see this in 1993, National Weather Service, Wilmington, Ohio, that was undergoing construction. And eventually this project was completed in 94. And this is kind of like how they are organized across the United States today, again, into these weather forecast offices. So with all of them constructed throughout the US, we now have a total of 122 NWS field offices, or WFOs, across the country. So this is just kind of a cool picture here of what the Weather Bureau office looked like back in 1926, excuse me, up into present day is a photo of what our office looks like from the exterior. So we'll go ahead and jump into the next part. So I always like to throw this whenever I give presentations, throw in the National Weather Service mission statement, because, ultimately the National Weather Service mission is to provide weather, hydrologic, and climate forecasts and warnings for the protection of life and property and the enhancement of the national economy. So it's always important that I share that with people because, again, one of the biggest things that we do is really trying to serve you guys and provide the best weather information that we can and to try to make everybody weather aware and build a weather ready nation. So the cool thing about this field is that, so we are a government entity. So we kind of, there's a tree kind of put together here where you can kind of follow down and see where we land sort of within the government. So we do fall under the Department of Commerce. So within the Department of Commerce, you have the National Oceanic and Atmospheric Administration, or NOAA, which you may have heard before. So within NOAA, you have all these different agencies, but National Weather Service falls within that agency. And specifically the weather forecast offices, again, are a branch or sector of the National Weather Service. But the National Weather Service doesn't just stop there. We have all different sort of agencies that differ than the WFOs ourselves. So like the Storm Prediction Center, the Weather Prediction Center, the National Hurricane Center. Those are all agencies within the National Weather Service as well. So WFO Wilmington, our office is staffed by 24 full-time employees, and the office is always staffed. So weather never sleeps, and neither do we sometimes, at least it feels like. So we always have people that are in the building. Even for the midnight shift, we usually have at least 2 people that are in there at one time. And staffing levels can always vary depending on the weather situation. And as many as 8 to 10 meteorologists can be on site during severe weather events. This past event that we actually had in December, even overnight, we had 7 people staffed up. So it can be challenging for sure at times. Your schedule can kind of get disrupted if you sort of have a severe weather or any sort of active weather pattern that's expected to move in. But that can be in some ways the fun of, or the excitement of the job. So here's a map of the United States. You'll notice it looks maybe a little bit different than what you're accustomed to seeing. But this is just kind of showing the breakdown or layout of all the WFOs that are scattered across the country here. And so here we are at Wilmington, Ohio. And you can see that based on the county warning area that we are covering, it's not just in Ohio. So we do have a few counties that we do cover in portions of Indiana, Kentucky, and then the bulk of them in Ohio. So we do have a total of 8 counties in Indiana, 12 in Kentucky, as well as 32 total in Ohio that we are responsible for. So again, I mentioned Wilmington. One of the reasons they picked it is because it's kind of in a good middle ground area between Cincinnati, Dayton, and Columbus. What makes Wilmington also kind of unique is that it's sort of in the middle of nowhere. And the reason I say that is because whenever you have a weather service office that is put in a location, one of the biggest things they have to think about is the radar. And most weather service offices are going to have the radar on site because it just makes it so much easier for like electronics technicians. They have offices as well. And it makes it a lot easier for them to be able to access the radar if they have to do any sort of repairs or updates or anything like that. And if you think about it, you do have offices in Cleveland, but even their office, you really won't see weather service offices located in like the middle of a downtown area. And that's because if you think about what a radar is doing, and we'll talk a little bit more about radar later, but it's scanning 360 degrees and then going up in elevation and scanning 360 degrees again. And if you were to have tall buildings or trees or anything like that that are obscuring its vision, you'd basically be getting poor data quality back to the radar product that you're looking at.
Hey, Logan.
Yeah.
So do they also seek the high ground when they're trying to locate an office?
No, that's a good question, and I do think that they will also kind of look for that as well. They're basically just trying to make sure that you're not in a location where you're going to have, like I said, tall trees or buildings around. So elevation definitely plays a factor in that. And if you can play now, you don't want to be too high in elevation, because the lowest radar scan is actually at a 0.5 degree elevation angle.
Oh.
So it's almost like horizontal, but a little bit up. So just a half degree tilt higher is where the sort of scanning begins. So if if you have it too high, then you can miss some of those low level features. So there's sort of a balancing act that you have to kind of figure out. And that's always one of the things that makes radar so challenging is, the further you are away from the radar is going to end up scanning and potentially missing some of the low level features the further you go. So again, with Wilmington, the whole idea was that, well, let's put it in a location where we can get fairly good coverage of our 3 major metropolitan areas. But no, that's a really good question. That's, something that they have to take into account, the elevation. But again, there's always that balancing act that they have to sort of figure out in the process.
Don't you also get false temperature readings in a metropolitan area? You get kind of a temperature difference because you are in that area. So depending on what you want, if you want to do general forecasting of the overall weather pattern, I would assume that'd be a problem.
No, that's a good question. It definitely can depend. A lot of our weather stations are located. We have a lot look like sporadically, but as far as like in the metro areas, we keep them at the airports, and they're kind of owned and maintained by the FAA. So the whole idea is that they're sort of quality controlled because you don't want to put a weather station like over blacktop, because like you said, there are certain things about metropolitan areas where you can get sort of erroneous data. If you were to put the weather station over blacktop, your temperature readings could be 10, 20 degrees warmer than what it really should be. And so they have different techniques too. We're actually not measuring air temperature immediately at the surface, but we're actually measuring air temperature usually about 3 meters or something like that off the surface, 2 to 3 meters. So you're not getting sort of the influences of concrete or pavement or anything like that too near the ground, where it can sort of create some of those like erroneous data values there. So they have quality control things that they do to make sure that the equipment is up and running okay. But yeah, like you said, there's certain areas where they will not put weather stations, and that's because of the influence of pavement, blacktop, and other things like that that could create errors or false numbers, so to speak. And I apologize if you hear my cats. They are currently scurrying across the floors and chasing each other.
So yeah, I think you're implying, and I think I've heard this, and I hope I'm not stealing future thunder from your presentation, but that the office is where the radar sits, but you guys have small weather stations that pick up temperature and basic weather facts scattered all over the place, correct?
That is correct. Yeah. Yeah. So we have like one station at our office, but basically at every single airport or airfield, we also have a weather station. So even at like Dayton, Wright Pat, and like CVG, we have one there. And then we have a lot of stations too in just kind of like major cities. So like even some of these cities you see scattered across the map, Newark, Springfield, Chillicothe. There's a lot of actually weather stations that we have kind of scattered throughout. Some of them, majority of them are actually kind of operated and owned by the FAA, but some of them are owned and operated by the National Weather Service. So there's kind of like a joint effort there. So this is just kind of like a photo of what the operations look like inside the office here. So each different workstation basically has a different role. So we all sort of work together, but we all play our own sort of individual roles or part into basically creating forecasts, disseminating products and different things like that. So One desk is going to be responsible more for like aviation products, and I'll talk about some of these a little bit more in depth. One is going to be looking at severe weather and hydrological watch, so that might be the desk that focuses a little bit more on radar, and then also managing, flood products and making sure that flood advisories, flood warnings, and things like that are put out in a timely manner. The long-term forecast and the short-term forecast. So we have two desks that are specific to just kind of creating the forecast. So one focuses more on sort of the short term, like the 48-hour period, and then one focuses on like the 3 to 7 day forecast. And then a public service desk. So this one is kind of like the jack of all trades. They'll work on stuff with the NOAA weather radios. They might do stuff with social media, taking phone calls and different things of that nature, issuing storm reports, and so on. So our public forecast, these are routine forecasts, something that everybody is kind of familiar with. So, again, we're responsible for issuing these actually roughly about every 3 hours. Sometimes we'll update them a little bit more frequently, if we have really active changing weather, whether it be an evolving thunderstorm, or even like a mixed precipitation event where you might have a transition of like rain to freezing rain to sleet and snow. But the routine variables that we forecast for are kind of listed at the top here. So like winds, cloud cover, temperature, visibility, dew point, a lot of things that you guys might be familiar with there. Oh, and then, so I did kind of mention, but again, we have a short-term forecaster and a long-term forecaster, and that's kind of always the case. So the short-term forecaster, you notice that they only forecast kind of for like that first 48-hour period. Whereas the long-term forecaster basically takes days 3 through 7. So the long-term has more days than the short-term, but that's really because we have our highest confidence sort of in that now to 48-hour period. And so we like to put as much detail really as we can in that first day or two, because that's when we have, like I said, the highest confidence in producing a more accurate forecast. And of course, that's the thing that, people care about now, what's going to be happening today or even tomorrow, more so than maybe 5 days out, at least just kind of, thinking about more than near term stuff. So the other thing that we are responsible for is issuing those watches, those warnings and advisories. So if you're watching the ball game and you see tornado warning pop up on your screen, that was unfortunately issued by us. But we issue these watches, warnings, and advisories for a lot of different products. Some that you may not see very often. There are even products that I haven't listed here, but you might see issued out maybe more so in the Central Plains, where they might deal with more fire weather stuff or other various things. But like winter weather, dense fog, wind, flood, heat, we have products for all of these things. So once we are looking at basically certain thresholds for all these different weather phenomena, we then are required to coordinate with our partners around us, all the other forecast offices, and then issue these basically as needed. So some of them are sort of like short fuse products, like a severe thunderstorm warning, a tornado warning. Those are kind of short fused. It's kind of happening immediately right now. Take action. Some of them a little bit more longer fuse, like a watch, or even if you're just issuing something like a heat advisory, it's over the course of the day, or at least over the afternoon. So a little bit more longer fuse there. One thing that is kind of interesting, and I wasn't too familiar with this before I got in the weather service, but one thing that we don't issue just immediately by ourselves is like a severe thunderstorm watch or a tornado watch. So these are actually done primarily, these two products, they're done by the Storm Prediction Center. And then what they do is they basically, we'll do a video or a conference call with them, and they'll say, hey, we're monitoring weather for the day. We feel that these counties in your county warning area could be affected. And so here's a preliminary map of where trying to draw up, the tornado watch for the day, and what do you think? And so we can kind of give our 2 cents as well. So there's a lot of coordination and collaboration that does go on in the Weather Service. Again, not just between us and surrounding offices, but between other agencies as well, such as the Storm Prediction Center and even the Weather Prediction Center for other things too. So another thing that we do is issue these aviation forecasts. So as I mentioned, we have weather stations located across several different airports and airfields across our region. But we do make routine aviation forecasts for a total of 6 different airports in our area. So that includes CVG or Cincinnati Airport, Lunken Field, Dayton Airport, Wilmington, Columbus or John Glenn, and then Rickenbacker. So the unique thing about our aviation forecasts is that these are done just 4 times throughout the day. And so we forecast some of these listed at the top here, some of these parameters are similar to what you saw for a public forecast, but some of them differ a little bit too. So, aviation, they care about different things. They may care about temperature a little bit when you're talking about, potential for like frozen precipitation or whatever. But really the things that they want routinely are things like wind speed and direction, cloud cover, and specifically heights above the ground. So one of the things we do is we're actually forecasting where do we think the height of a cloud will be above the ground, which is as difficult as it sounds. But at certain thresholds or certain levels, the thresholds change, and pilots might need to use or rely more on their instruments to be able to take off or land the plane. So that's why they care a lot about cloud heights above the ground, and visibility as well is another big thing. Wind shear they're interested in, so that's kind of just looking at a change in wind speed or wind direction with height. And then, as I mentioned before, precipitation. So those are all things that we kind of provide in those routine forecasts for them.
Logan,
Yeah.
do you mind saying a few words about wind shear, what its definition is? I remember people talking to us in aviation school about avoiding downdrafts, obviously, but I'm not really sure about wind shear. It was a long time ago.
And how you detect it, I'd be interested in hearing also.
Ditto.
Yeah, absolutely. So the wind shear by definition is basically just a change of wind speed and or wind direction with height. So basically we're just what we're doing is we're forecasting, okay, well, so one thing that we give them is the wind speed and direction, and I guess I should have clarified here, but that's like at the surface. So they want to know, near the surface when they're taking off landing, what can be the expected wind direction and wind speed, because that might affect where they want to land. Different airports have runways that are oriented in different directions. So if you have a really strong northerly wind, you don't want to land on a runway that's east and west oriented, because you can veer off of, the track there. So when we're looking at wind shear, well, we're forecasting what the wind speed and wind direction is going to be, right at the surface. But then we're also looking at model data to determine what the wind speed and wind direction is going to be, roughly about 2,000 feet or so above the ground level. So pilots can experience turbulence, further aloft, where you might experience a little bit of that wind shear. But they care a little bit more about the wind shear closer to the ground as they're landing, because they don't want to get in a situation, again, when they're trying to land and you've got wind that's going, like a strong, maybe southerly wind to start, and then it shifts to the west. So they have to kind of plan, again, which runway they're going to potentially try to land on and different things of that nature. I can't speak to what all they do, but that's essentially what we're doing. We're just trying to basically give them, okay, is there going to be a significant change in the wind speed and wind direction in the, from the surface to several thousand feet off the ground? And really, we're just looking at, primarily 2 or 3 different levels. We're looking at what the wind speed and wind direction is going to be at the surface at 2,000 feet, and maybe roughly about, we say like the 850 millibar level, which can be anywhere from about 3,000 to 5,000 feet above the ground. So no, that's really good. Go ahead. Yeah.
How is it detected or predicted?
It is so there that I
At
yeah, I guess I
altitude.
should have clarified. They are looking for so if you have 40 knots of wind shear, meaning that let's say you have a surface wind of only about 10 knots, and knots are fairly similar to miles per hour. There's just a few it's off by just
It's a different unit of speed. Yeah, got it.
correct, yeah. So if you have 10 knots at the surface or even 10 miles per hour, and then you have 50 miles per hour, even if it's 5 miles per hour southerly wind at the surface and 50 miles per hour southerly wind 2,000 feet above the ground, that threshold right there is a difference of about 45 miles per hour. And anything over about 40 miles per hour is when they care about us forecasting low level wind shear.
So
'Cause if
I'm
that-
sorry. I was actually trying to ask literally, how do you detect the wind direction at altitude, or how are you determining what the wind direction is at altitude?
So that's just given us through model data.
Okay.
We're in these weather models, you're able to diagnose. So they break down different layers essentially of the atmosphere. And I'll talk a little bit about modeling too here later on in this presentation, but these models are not just forecasting parameters at the surface, but they're also forecasting at different layers or levels throughout the entirety of the troposphere.
Got it.
And so by doing that, we're able to look at, okay, well, at this layer, and we usually look at it at like a pressure level. So at about 850 millibars, which like I said, would usually be several thousand feet off the surface, here's what temperatures will look like. Here's what winds will look like, and different things like that. Here's what relative humidity will look like. And so all of that would be important to kind of diagnosing, different features and things that change, not only just winds, but temperature and thermal profiles through the atmosphere. So, and then one other way that we measure that, which I'll talk about too here in a little bit, is with us launching weather balloons. And that does a similar thing where we're kind of creating this 3D structure of the atmosphere and looking at changes in wind speed and wind direction and temperature and different things like that too. So
Maybe at some point related to Steve's question, it would be nice if you'd say a little bit about what gives you a radar return off of weather, and is that useful? I mean, we'd like to hear a little more about radar, I think, and what your radars can do for you. My impression was that some information about wind shear was determined via radar, but I may be wrong on that.
you can determine actually some, so radar will give you, it's called this vertical azimuth display. And you can get wind estimates essentially using radar as well. So that is definitely a tool that can be used. And I actually do have a section here on radar. So maybe I'll go through that. And then at the end of the presentation or even at the end of radar section, if you have additional questions about how it relates or like other radar features or products, I could address it a little bit later down the road if that's okay.
Thanks.
That sounds great. And Logan, I will remind you, we're a very technical minded crew, so feel free to dive in a little bit to the science. We're happy to hear and learn that. So
Yeah, no, absolutely. Well, cool. So that actually takes us into our next sort of section where I'll break down a little bit more about how do we make our forecasts. So two primary ways of making our forecasts are through the use of observations, which are absolutely one of the most critical things to do because you can't run weather models without observations. And then of course, the second part I'll talk a lot more about later is numerical weather prediction, which is essentially modeling. So again, some of the ways that we take observations are through these surface observing stations or weather stations, through the use of radar, satellite data, and of course, weather balloons. So these surface observing stations, again, these are basically like the weather stations. Whenever I say weather station, I'm referring to these these stations here specifically. So these stations are basically providing routine data, a list of all these different variables that are collected or shown here. And they provide data actually every single minute. So they're frequently providing updated information about things such as wind speed and wind direction, humidity, temperature, dew point, and different things of that nature. So that we are able to kind of see in real time, the frequent changes that we're observing at these stations. And that's absolutely critical, not just for, being able to observe what's going on, to see it, that our forecast is verifying, but for also things like when you see a thunderstorm coming in, and we're trying to decide, okay, well, is it severe? It's close to the thresholds, not quite sure. And then all of a sudden you see a weather station that has a 65-mile-per-hour wind gust, and we're like, okay, yeah, it's severe. And so they are absolutely critical. And again, the more weather stations you have, the better it is for us as meteorologists to be, more accurate in putting out products such as severe thunderstorm warnings and different things of that nature too. So these can help us in a lot of different critical situations. And the cool thing about these too is that they can also detect lightning and the amount of freezing rain that is accumulated on a flat surface. So when we're looking at all these weather stations, again, when they're plotted on a map, it can look pretty messy. But there's over 900 ASOS stations. So ASOS is basically just abbreviating this, so it's Automated Surface Observing System. So there's over 900 of these nationwide. And again, each one of these, when they're plotted, it makes it nice because you're kind of able to see and diagnose different things such as areas of higher and lower pressure, as well as where your frontal boundaries might be. So you can much easily detect where your cold fronts might be or your warm fronts. And that's all critical when we're forecasting, for you guys. So the station that's plotted here, I just kind of pulled it up here. But again, when we're viewing these surface plots, they're kind of nice because they're providing a lot of information sort of compacted into just one little plot. So one location here, you're able to quickly diagnose and see what the temperature, the dew point temperature is, sky cover, which is basically determined by how many or how much is filled in with this little circle right here, the air pressure, wind speed, and wind direction. If precipitation was also occurring, or there were low clouds or visibility reductions, there'd be additional symbols that would be located on these plots here. So this is a great way for us, again, to just kind of quickly look at and diagnose, okay, what's kind of going on. It's helpful too to get like not just a specific point and see, okay, what's happening at Findlay or what's happening at Dayton or Cincinnati, but to kind of look at the broader scope of things too. And again, to detect and identify where our pressure centers might be or where the cold fronts are located. So this is one of my favorite things I like to talk about is the use of weather balloons. So one thing that our office does, and not every single weather office does it, but we launch balloons, weather balloons twice a day. And this is done at 92 different sites across the US. So again, I mentioned that there are 122 WFOs. Well, only 92 stations do it across the country here, but one of them does happen to be Wilmington, Ohio. So with these weather balloons, you'll notice that there's a parachute that's attached to this weather balloon, and then attached to this parachute is an instrument that's called a radiosonde. And so the radiosonde is the instrument that's collecting routine meteorological variables such as temperature, moisture and dew point, wind speed and wind direction, as well as atmospheric pressure, basically from the point that you launch it to the point where it pops. So as these balloons are ascending, they actually ascend at about 1,000 feet per minute. And commonly we can see these balloons reach upwards of about 100,000 feet or potentially more. Usually in warmer air masses, you can see those balloons rise a little bit more, and that's just because you have less pressure that's basically being pushed against you or pushed against these balloons. And they usually last up to about 2 hours before bursting. So where they're popping is essentially like usually in roughly about the tropopause. So we say that all weather occurs in the bottommost layer of Earth's atmosphere, which is the troposphere. And so we're collecting data basically from the surface all the way through the top of the troposphere. And again, maybe even a little bit extra into the tropopause there, because usually at some point you start to see temperatures decrease, generally decrease unless you have some interesting weather phenomena that's occurring, but they decrease with height all the way throughout the troposphere. But in the tropopause, those temperatures start to, steady out a little bit more before increasing more in the stratosphere. This is the instrument, like I said, the radiosonde, which is collecting these routine meteorological observations. And actually later this year, I'm going to have to update this photo because we will actually be getting a different looking instrument than the one that is showed here. But currently, this is still the one that we're using. This instrument, or this part of the instrument right here, is the thermistor. So it's a small, this is basically what's measuring the temperature, but it's a small electric current that's transmitted across the wire. And it's the resistance of the current that is actually measured, which is a function of temperature. So it's not like we're sending a thermometer up there, but instead we're actually using what's called a thermistor. And so with this instrument, we're able to measure what the temperature looks like. This instrument right here, or this part of the instrument, is the humidity sensor. So with the humidity sensor, there's a direct relationship between relative humidity and the sensor's capacitance. And this relationship is at the base of the operation of a capacitance humidity instrument. So within the styrofoam portion here is the pressure cell. So that's, like I said, it's contained within the radiosonde body unit. And so that's what's going to be measuring our pressure as we go up in the atmosphere. And with each of these instruments, we have GPS that's incorporated into the instrument. So we actually measure both wind speed and wind direction through the use of GPS. So depending on how fast the instrument travels up vertically in the atmosphere, as well as horizontally away from the office, that's essentially how we're able to measure both wind speed and wind direction as a unit of time. So once we get all the,
Could you say a little more about, I'm just curious about the capacitance sensor, how that works? Is the equivalent of a wet bulb or something where it's got a capacitance, which is at 100% humidity versus the atmospheric, or how, I mean, I'm just trying to figure out how it works to give relative humidity in a capacitance sensor.
Yeah, I'm not super well versed in the sensor itself, but I think that essentially it works similarly as like a thermistor, but it's able to detect the I think the weight of the moisture that's essentially being pushed down on it, and so that's where the capacitance kind of comes into play. So depending on the weight of the moisture that it's detecting, that triggers like a change in it. And so from that, it's able to then actually measure what the relative humidity is in the atmosphere. And then from the relative humidity that we get, we actually then calculate what the dew point temperature is based on the relative humidity.
Okay, all right, thanks.
Yeah.
What's the gizmo on the top there that you don't have an arrow to?
Let's see here. Like
the tube looking, yeah, that thing.
Oh, this? Oh, no, that's a good question. It's funny with these instruments, we actually have, so it's really hard to see here, but this text right here says harmless weather instrument. And then there's like a little description there where we talk about what this instrument is and what it does. The tube here on the top is actually a little piece of paper that's tied up, and you might be able to make it out here, but it says it's like mailing instructions. So we
Excellent.
yeah,
Okay.
yeah.
This
so
is
we-
not from Mars. Please send it back to the National Weather Service. Got it.
Yes, exactly. So it's basically like, hey, this is one of our instruments. If you get it, feel free to, send it back to us, and we'll try to reuse, whatever we can from it.
What percentage do you recover?
Oh, 0.5%. It's not very much. And you got to think about, some of these instruments are kind of landing out in fields. We actually have had people call us and say that, your instruments landed on my cattle, and they kind of throw a fit about it, which is just kind of the unfortunate thing with these. But, the fact that they are very lightweight and styrofoam, and there's a parachute attached to them, they really do land at a speed that doesn't really harm anybody or any sort of wildlife. But we don't get to choose where they land. It just depends on where the wind's blowing. Of course, most of these are going to, eventually at some point you probably get more of a prevailing westerly wind. So generally speaking, these instruments are going to move, east of the office. But yeah, so we do have mailing instructions that are attached to these instruments in case people get them and are willing to send them back in. If they don't, we say that, you're also welcome to keep them as a souvenir if they like. And some people do.
I don't want to go too far astray here, but I am also curious. The balloon,
Mhm.
that's a fair amount of fabric, or I'm not sure exactly what it's made of, but once it blows, does that shrivel up to something small, or do you have a bed sheet landing in somebody's field?
No, I don't know exactly what it looks like when it pops. I have heard that these balloons can actually get as large as like a 2-story building before they pop. So yeah, they are very large. They're made just from latex. So I guess the hope is that, even when they pop, they're still tied up with string, and that you don't have, it's not like confetti where, the balloon pops and you have a bunch of pieces go everywhere.
How big are they before you inflate them? Like, how big is the deflated balloon?
Trying to give a good example. Well, at least in terms of like maybe height. So if I were to hold a balloon next to me, I would say usually that they are probably about 4 feet tall, and probably close to about 3 feet wide.
Some more like a towel than a bed sheet.
Yeah.
Okay.
So they're pretty good in size. No, and let's see. I think I have a picture. Well, yeah, maybe that'd be a good thing to add in for future reference, is have somebody holding the balloon, and then you can kind of get a good idea of what it looks like, because man, they can be very awkward as you're trying to launch them. And if we are launching these weather balloons in really windy weather, you got to be careful, because as you're launching the weather balloons, you essentially have the radiosonde in one hand and the weather balloon in another hand, and you launch the balloon and you got this, piece of string that's attached, and you got to kind of wait for this, the string to go up with the balloon itself. But when it's really windy, well, what can happen is that balloon can veer sideways, and if you get to the end of the string and you have to let go of the radiosonde could then go sideways and hit the ground. And you got to be careful there, because as soon as it hits the ground or anything like that, it can start to mess with the temperature sensor and things like that. So you may have to do a second launch, which is unfortunate. But we will use sometimes a different device where it's like, instead of using a long piece of string, your string is basically like, it's a thinner string, but it's like all wrapped up already. And then you just basically tie the balloon to this. And so you'd let the balloon go. And when the other piece that you're, attaching it to, when that goes like immediately with it, but the string will actually unravel then essentially when it's going up after you launch it. So that makes it a little less awkward for doing like weather balloon launches when it's really windy. So otherwise we might have 2 people doing a balloon launch. So you just gotta, do whatever you can to make sure that you get it up successfully.
So Logan, instead of just asking, I actually looked it up, and the capacitive sensor means that it has a water absorbing dielectric. And so the capacitance changes with humidity. And the thing I was trying to figure out was relative humidity, and the answer is actually very simple, which is as long as you know the temperature and maybe the pressure, if you want to get really refined, you can always calculate 100% saturation from a table. So therefore you can know the relative humidity. You get the absolute humidity, if you will, but then knowing the temperature and effect, what the total saturated water pressure would be. So
Yes. Yeah. Well, thank you. Yeah, for looking at that. And yeah, I guess I should explain the relative humidity portion of it a little bit better. But yeah, relative, that's the thing about the word relative and relative humidity, is that it's dependent upon what your ambient environmental temperature is. So yeah, good call there. So with this weather balloon, like I said, when we're launching it, we're measuring all these different variables. And so the way that we plot these variables is with what's called a skew-T log P graph. And so in this graph, we have, the wind is all the way on the far right side. So it's sort of attached, but not necessarily in the portion of this graph where we have some of these different parameters. But we're basically able to see the wind. So here at the surface, we can see that there's basically a northwesterly wind of 10 knots. So the really long bars indicate that a wind speed of 10 knots. And then sometimes you just have to count them. The small ones indicate 5 knots. And then the triangles indicate 50 knots. So we're able to see, like I said earlier, with the weather balloons, we're able to basically look at how wind speeds are changing from the surface all the way up through the depth of the troposphere. Additionally, we're also able to see how temperature and moisture behave in the same fashion through the depth of the troposphere. And we're able to look at all the different pressure levels, that these variables are changing through the troposphere. And these skew-Ts are just one of the most critical ways for us to diagnose the atmosphere, because we're able to determine a lot of things from it, not just like what the surface, temperatures look like, but, depending on the thermal profiles with height, we're able to determine, where clouds may form, depending on if your temperature and moisture approach each other really closely. You might be able to determine, okay, this is a layer where we might have clouds. Or for winter weather applications, skew-Ts are absolutely critical for trying to determine what type of precipitation you'll receive at the surface. So if you really have, if you're really cold throughout a good depth of the troposphere, but you have a big warm layer near the surface, that's going to indicate that those ice crystals that are falling are going to be melting as they fall through this warm layer. And depending on the depth and strength essentially of the warm layer, it might determine whether you'll have partial melting or full melting. So that'll determine different things like, whether it's going to be sleet that falls at the surface or potentially freezing rain or different things of that nature too. So these types of graphs are very essential for determining all different types of potential weather hazards, not just winter weather, but even severe weather too. We can kind of assess and determine the amount of instability. And the nice thing about the computers that we have now is that based on these thermal profiles that we get in the skew-Ts, they can calculate a lot of different things that we use to measure, different variables that we may not get just from that we're measuring specifically like temperature, but we can measure things like the convective available potential energy, which that's a parameter that we use to essentially assess the amount of energy or instability that's available in the environment for updrafts or thunderstorms to essentially work with. And then determining different things too, so I mentioned wind shear earlier with aviation. Wind shear is critical for determining potential severe weather hazards as well, including tornadoes. So you can't have tornadoes without wind shear. And in fact, you really don't you don't have at least strong thunderstorms without wind shear. So thunderstorms that are stronger in nature tend to have fairly strong wind shear with it. And with the stronger wind shear, if you think about what's happening with the winds, again, if you have westerly winds at the surface and those winds get a lot stronger with height, what you're going to get is essentially the cloud as it's forming is going to be tilted. So when you get that tilted updraft, you actually get a separation of your updraft and your downdraft portion. And that allows for thunderstorms to essentially maintain and live longer. Whereas if you basically had like no winds, which sometimes we can get that a lot in like the dead of summer, like July and August especially, where you just get weaker winds aloft. You don't have the influence of sort of the jet stream or the polar jet nearly as much in the dead of summer here in the Ohio Valley. You get a lot more of those sort of, we call them popcorn thunderstorms or pop-up thunderstorms, where they pop up or tend to be short-lived. And that's because you do have that updraft and downdraft that get co-located. So there's no tilt there in the updraft and downdraft to essentially separate themselves. So where you have air being fed into the thunderstorm with the updraft and then the downdraft where the rain's occurring, the thunderstorm is essentially like killing itself, I guess, in a way, because where you're ingesting, like I said, all that moisture and warm air is where the precipitation ends up falling. And so those thunderstorms tend to be, shorter lived. So I just kind of want to talk about that. I know you guys said you like some of the more technical stuff, and I didn't really include a slide on that, but that's just kind of attesting to the critical nature of, not just doing these weather balloons, but looking and assessing all these different variables that we get from a plot, such as the skew-T. So as I kind of already alluded to a lot of these, but again, some of the different things that weather balloons can help us determine. Based on the temperature profiles, we can determine the amount of stability or instability that's present in the atmosphere. So again, moisture profiles, we can detect different things such as like cloud layers, and it also impacts the air density. Precipitation type, so again, determining at the surface whether we'll see rain, sleet, or snow, and then of course that wind shear, like I mentioned. So here's just a photo of what it looks like inside the inflation shelter. Nothing too exciting, just kind of like a giant garage. But again, you have to have that garage, tall enough so that we can get that weather balloon out comfortably, because we don't want to basically have that latex balloon touching anything, because there's always a risk of it, potentially popping there. So just a quick map here showing all the different weather balloons that are located across, weather balloons, the weather balloon launch sites that are located across the US. So here we are at Wilmington. You can see that, some of our surrounding offices, Cleveland, Northern Indiana, Indianapolis, and some of our partners down in Kentucky as well, they don't actually do weather balloon launches. And some of the reasoning, I don't know all the reasoning, but I know some of the reasoning is that these offices just aren't as in a favorable location to do launches, meaning that they might have a lot more like smaller or medium-sized trees nearby, or other sort of obstructions that don't impact the radar, but they could impact the weather balloons as they launch. Because again, you want, for the most part, generally an open field to launch these weather balloons, because if you were to have even some small trees nearby, again, if you have a really strong surface wind, that could blow it, right into any sort of obstructions. So part of it's that, and I'm sure part of it also has to do with funding and different things of that nature as well. Okay, so let's talk a little bit about radar. Radar, for those that don't know, it actually stands for radio detecting and ranging. And so at each Weather Service office, we have what are called WSR 88Ds. So those are WSRs, the weather surveillance radar. And each site here that's listed. So like I said, each WFO is going to have a radar that's stationed either on site or not too far away from that site. I do know that we have an electronics technician that's from originally from Alaska, and he worked at a site there. And he said that to get to their radar, they actually had to drive like 30 minutes or something like that up through like treacherous roads up a mountain, which just sounds awful. I don't know why they planned it that way there. So there are some instances where, you know, your radar is not going to be on site, but majority of locations do have, or majority of WFOs have the radar station there. And so you can see, I like to show this map because it shows sort of like the coverage that we have with these radars below 10,000 feet. And I show below 10,000 feet, and we use that sort of as a critical level because that's where a lot of your like more interesting phenomena occurs within thunderstorms. Now, thunderstorms can tower to over 30,000 feet. But these smaller processes that occur in the lower levels are absolutely critical. And really, the more critical level for tornadoes can even be as low as below 4,000 feet. And so you can see that, fortunately for us, we have really good coverage below 4,000 and even below about 6,000 feet, really through a good chunk of the Ohio Valley there. And as you move further west, there's still pretty good coverage when you get into the plains. You know, there's the plains, there's such a large region to cover there that it's a little bit more spotty. And of course, when you get sort of even further west, you're dealing with the mountain ranges and different things like that make it more challenging to be able to have radar coverage in those locations. So when we talk about radar, again, with radar, one of the things that people are probably most familiar with is the reflectivity. So reflectivity is kind of what we would see when we're looking at basically like precipitation intensity. So ultimately what reflectivity is it's representing the portion of energy that is returned to the radar back from scatterers. And scatterers, we just use that as a word for different things like hydrometeors. So things like rain, snow, sleet, hail. But when a radar scans stuff, as you might be aware, we're not just scanning, it's not just picking and choosing like the meteorological phenomena such as rain and snow. We actually get non-meteorological phenomena too that the radar ends up scanning. So things such as debris, dust, birds, insects, different things of that nature, the radar is able to pick up and detect that. So again, these radars are sending out a beam of electromagnetic energy. And when that beam is sent out, it's basically sent out, and whenever it hits an object, basically the object absorbs that electromagnetic energy and then re-emits it in all directions. And
Logan, do you tune the radar to the edge of some rotation band for water in the microwave spectrum, or are you just depending on, just the physical presence of the droplets to scatter radiation?
Excuse me. I'm sorry, could you repeat the question?
Water has an extended rotational spectrum from the IR down to the microwave. And I always wondered, are weather radars tuned to, be especially reflective for water? You could do that by being near an absorption band. I don't know a lot about the spectrum. I just wondered about it.
Yeah, so we use the S band, if that has any sort of use, I guess, for you. So the S band is the primary band that's used.
Yeah, that's the band of radiation. Use a band of frequencies. I was wondering if the frequencies were selected with the properties of water in mind, but I'm guessing that might be difficult because I think the S band is invariably far into the microwave. Oh, okay, never mind.
It's about 3 gigahertz, Dave.
Okay, that's by rotational standards, I think that's pretty low frequency. All right, never mind.
Yeah, so I guess the answer to that would probably be no.
Yeah,
Yeah, so they just use the S-band as far as I know, for these weather surveillance radars.
Well, just make the comment that microwaves, your normal kitchen microwave runs usually around 2.5 gigahertz. So it may very well be that S-band does absorb a fair amount of water, water energy. It's
Yeah.
pretty close.
Well, thank you guys for that insight. Yeah, I mean, it's there's always so much to learn and know about meteorology. I mean, you think about some of the basic stuff where you're just kind of learning about how weather works, but there's all this stuff. Radar is it's a whole, I mean, field of its own that it could be.
Since I asked a bad question, it occurs to me I should correct myself. Your nice comment about the microwave reminded me. The microwave frequency is not tuned to a water absorption band. I always assumed that, but that's not the case. And now that I think of it, its frequency range is probably well below what water absorbs. So I'm sorry, I should have thought about that more. I'm done.
Well, wait a minute. I may not be tuned. I'm sure it's a historic fact why they use the microwave band they do in the microwaves. But I mean, the fact is that's how it works. It absorbs, the water absorbs the energy from the microwave in order to heat things. So
Yeah,
whether it's well tuned or not, it works.
Yeah, it works. It's a lot of things beside the water absorbing the radiation.
But water does absorb it. So
yeah, the water does absorb it, but you're in that band of the microwave because it's easy to get high intensity at that level.
that's right.
And also there's the dielectric, you're in a dielectric absorption range. So a lot of different materials have dipoles that will oscillate in that frequency. I'm sorry, I'm remembering a paper somebody shoved under my nose about this. My apologies, I'm done.
No.
I'll toss a lower brow question at you. How many birds does it take before it shows up on radar? Like, does that happen? Do you see flocks go by, or?
We do, especially when you're kind of getting into the winter time frame. A lot of times you'll see, more clusters of birds that are just flocking south, right? I mean, so depending on the time of the year, you might see more than the others. And usually in clearer air, so when we run our radar in what's called clear air mode, it's a lot more sensitive to various things. So usually when we're trying to detect snow, because snow, those ice crystals actually, they don't return actually nearly as much energy compared to raindrops or larger balls of ice like hail. So we'll put the radar in this like clear air mode. And it makes everything more sensitive to what the radar is able to detect. So that helps with snow. But if you're like on a day like today where it's nice, pretty blue sky out, you have it on clear air mode, it's more likely than not that you'll probably be able to pick up, that is a really good question. I don't know how many birds like it would take.
But you can see flocks of birds migrating in certain modes.
You absolutely can. And in the morning too, a lot of times you can see clusters of like insects and stuff. And we'll have people comment on social media and be like, what is this? They'll see, radar reflectivity showing up. But it's, it doesn't look very meteorological. And actually one of the tools, and I don't think I covered in this specifically, I have one slide that incorporates it, but with these radars that we have now at the Weather Service offices, so they're called dual pole radars or polarimetric radars. And essentially what we're doing is we're scanning, so we're sending a beam of this electromagnetic energy in both the horizontal as well as the vertical. So sending a wavelength in those two different ways, I guess, you're able to kind of get a more 3D, more representative structure of what your scatterer might look like. And
You know-
so one of the ways that we measure that is through what's called correlation coefficient. And so correlation coefficient is basically like assessing the vertical wavelength to the horizontal wavelength. And for things that are non-meteorological, usually you're going to have a much smaller correlation coefficient, meaning that the things that are measured like horizontally versus vertically are going to be a lot different. So if you have like tumbling debris, that's going to be, you know, like a tumbling piece of wood, that's going to be measured a lot different in the horizontal compared to the vertical, just based on the length of the object.
That is so slick. We actually use a variant of that in the optical region for particle sizing. Rayleigh scattering versus other types of scattering do very different things with polarization. That's interesting. To follow up on Steve's question, do you get radar shadows? I imagine if a mile away, there's a hailstorm with, you know, baseball-sized hail coming down, does that absorb enough radiation that you can't see behind it?
So in a way, yes, we get things that are called 3-body scatter spikes. And so what'll happen is the radar will detect, and usually you get these, they're called 3-body scatter spikes, that you often get them with larger hail. So yeah, if you were to have like baseball sized hail, more likely than not, you're going to get those. And so so you'll kind of have this like elongated, so like in this picture right here, we've got a photo of a supercell that clearly does have hail and large hail with it, which is like these pink and white colors. But what you might have is you might see like this blotch of hail be stretched even further. And so that's kind of that erroneous part that's happening, is that it's so much energy that it's like falsely putting it even further like into the storm than where it's located. But usually that's like an indication. I mean, it's tough because it creates some false data, but in a way it's also the falseness of it. That's not a good word.
It's still information. Negative
Erro-
information is still information.
Exactly. It's essentially saying that, hey, we've got a like a severe storm en route. So in a way that, yeah, and that's some of the nuances of learning radar, is understanding the types of errors that you can have and what that means, because even bad data is good data in a way, if you know what to look for and what the information is providing, basically. So that's a really good question. Yeah. So I'll continue on here. So the only thing I didn't touch upon, which I'm sure many of you already read or kind of know about anyways, but whenever you're looking at reflectivity, essentially the warmer colors represent more energy that's being returned to the radar. So you get more energy from things such as heavier precipitation, of course, hail, even debris that's being lofted up and picked up if you were to have a tornado on the ground, and even melting snow. So those can all be good indicators of higher reflectivity. It's being shown on the radar. So this was kind of brought up earlier too with radar and its ability to detect motion. Well, we're doing that by determining radar velocity. So essentially radar velocity is looking at components of motion that are going directly toward or directly away from the radar itself. So motion actually cannot be detected from the radar if the winds are moving essentially like perpendicular to where the radar beam is scanning. So that's, again, one of the setbacks or unfortunate things that we have with radar, is that we're kind of, so that's kind of shown by this like grayish area here through the radar, is that this is kind of motion that's perpendicular to radar, so we can't actually detect what's happening, but around it we can detect, again, motion that's moving away from the radar in red or towards the radar in green. So yeah, so that's another way of showing, again, motion towards the radar is green, motion away from the radar is red. So even if you didn't have the point location of a radar, you could kind of determine it again just by looking at the velocity data itself.
So is that detecting, is it like getting returns and noting that the returns are, I'm trying to figure out how it,
I think it's Doppler.
It is
yeah,
Doppler.
it's,
Doppler.
Yes,
it's just that's, okay.
think of it essentially as like a cop's radar. So it's sending out a beam, and depending on the return speed of that that it gets, it's able to measure the velocity. So again, it's not a true wind
Doppler of
speed
the
estimate.
pings. Okay, all right, that makes sense to me now.
Yes, it's not a true estimate. It's just, it's using Doppler to, I guess it's not a true value. It's an estimate of what's occurring. So yeah. But the important thing about radar, again, is it's essentially allowing us to see into a storm. So with radar, again, and velocity is one of the most critical things, but we're able to detect, again, areas of convergence. So whenever you have these greens and reds that are sort of moving towards each other, so here our radar is located down here. Again, we know motion, or green is motion towards the radar, red is motion away from the radar. So if you have this occurring on sort of the same side of, where the radar is located, we know that there's this convergence happening, and convergence is critical to determine that, or potentially determining that, we could be looking at a potential tornado situation if the convergence orients itself in a way where you have sort of motion, sort of more of a circular motion that's beginning to occur with that. Whereas divergence is also critical because I think someone mentioned this earlier with like downdrafts, but that's essentially what we're looking at on this image to the right. So again, you have the radar located to the southeast, but you have these green and reds. So they're oriented in opposite fashion of what's on the left. But you can see that in this situation, you have the winds that are actually diverging away from each other. And so essentially what just happened is a downdraft occurred within the storm. So the storm sort of collapsed, but in its collapse, it's actually gushing out these really strong winds near the surface. And so that's essentially what we're picking up is an enhanced reading of the velocity here. And this is likely, reaching probably severe warning criteria.
So is the convergence necessarily an updraft then, or, I mean, it would depend on the altitude you're looking at, I guess.
Yeah, right, it would. Areas of convergence are basically just aligning, where you might have your updraft and downdraft in a similar area. But, ultimately, the convergence is kind of saying that, okay, we're taking two, we've got wind shear essentially that's present because as you're moving further away from the radar, again, you're going to be looking at winds that are, slightly further aloft as you go further and further away from the radar. So in this instance, you're basically saying that you've got pretty strong wind shear that's occurring. You've got winds that are moving into the storm at a lower altitude from the southeast, but from the northwest, just slightly higher aloft, you got winds that are moving toward, again, this sort of radial here. And because of that, that essentially is saying that you've got a veering or a change of winds with height there. And so that's something to monitor. That's essentially saying that your updraft can potentially be rotating. So
you that was going to be my next question. I was a little surprised by what I think your answer would have been. So I recognize as the radar is looking out, you said it's about 5 degrees at a minimum, and you do a sweep low and you do a sweep high. So there's an angle associated, a vertical angle associated with the sweep and associated with the data.
Correct.
I'm surprised to hear you say it doesn't sound like when you look at a plot like this, it's not correcting and giving you values at a flat plane at some altitude. this picture is actually including that upward sweep? In other words, the data you're seeing close to your radar tower is in fact lower altitude than the data you are seeing further away from your radar? Or does it correct to some altitude? Do the math to say, here's what it is at this altitude across my picture, my plot?
No, that is correct. So it is not putting it to like a flat radial plane or a flat plane or anything like that.
So it's kind of a slant range plot.
Yeah,
It is,
surprises
I guess,
me.
kind of in a way, yes. Now like over here, there wouldn't be a huge drastic difference. I mean, maybe a couple of 100 feet between these, the reds and the greens. But that is still, it's a small enough value where the analysis of it isn't going to change too much as far as assessing like convergence and divergence and whether or not we've got potential rotation.
So it's a shallow enough angle that you're not introducing, there's not that much altitude difference between where you are next to the tower and where you are. Well, let me ask that question. So I guess you had that on the plot before.
Yeah, I mean, if the distance between Wilmington and Dayton's about 50 miles and the slant range difference in altitudes are only a few thousand feet, the slant range and the distance along the ground are not too different.
Not too different, very small.
Right. I was
Sine or
wondering the same
cosine,
thing.
whichever that is. Right. Okay.
Yeah, no, these are all really good questions, and
It's all
Yeah,
mostly horizontal.
correct. So yeah, and like I said with the radar here, so this is a really good example. This is dating back to the if any of you guys remember the March 2nd 2012 tornado that occurred in West Union, Ohio. And so this is really zoomed in here, but this is a really great example of where you've got this. So of course you've got these red and greens that are sort of right next to each other. And not only that, but you see this sort of little kink that's located in these red and greens. And so this image here is basically indicative of a strong circulation that's occurring. And so this is an example of where we would say, hey, yeah, a tornado warning should probably be issued. We can't necessarily confirm from this image that a tornado is present or is on the ground, but whenever we say that, hey, conditions are right for a tornado to form, and we see this image in velocity, this is like the point where we would issue, a tornado warning, if not before this point. But this is a storm that did produce.
Sometimes I remember hearing, on television, a meteorologist refer to the vorticity that the radar was detecting. Is there a way to detect rotation in an air mass via radar? I'm guessing you would look at a correlation time for the return, but I don't know.
So the way that we look at rotation is essentially like from this image right here. So it's basically being able to detect. So we do have algorithms actually in our computers that kind of give an indication where there's what's called a TVS, so a tornado vortex signature, which is essentially saying that, hey, this storm has rotation that's present.
Yeah.
It needs to be looked at kind of in further detail. So we do have algorithms that run sort of in the background that are able to detect rotation. A lot of radar analysis is kind of done, though, more so just like with our own interpretation. So at this point, now we do have little tools that will also, so like we have sample tools on our computer where we can, so like as I'm hovering over this part right here, I can look at this and say, okay, so here we've got outbound velocities of, let's say 50 knots. And here we've got inbound velocities, the green, of 60 knots. So from those two, we actually then determine what the rotational velocity is with our inbound and outbound velocities right next to each other.
Uh-huh.
And by determining the rotational velocity, it's basically just taking the two, the inbound and outbound, adding them together and then dividing by 2. So you're taking the average. And that's essentially, you're getting your rotational velocity. And they kind of take you through radar training where usually 20 to about 25 knots of rotational velocity is enough to warrant a tornado warning, given that you're in an environment that is conducive to being able to produce tornadoes. Once you get to about 45 knots or so of rotational velocity, 45 to 50, that's the point where you can say, we can throw a considerable tag on it. Basically saying that there is strong enough rotation that not only can a tornado be produced if it's not already producing one, but that like a considerable tornado could be produced out of this.
So it sounds like you know what you're looking for in order for there to be a problem, but there's no aspect of the radar that says explicitly this air mass is rotating at a rate you should be concerned about.
Other than diagnosing, I guess, yeah, just like ourselves, you have little tools and stuff like that within our software where it might be able to also tell you that. But what's funny is that you'll find a lot of people that are working radar, they find it to be faster instead of searching around for these tools to hover over and quickly analyze themselves, because that's the thing about when it comes to radar methodology is that you just want to be as quick on your feet as possible.
And
I'm
I
guessing
don't doubt you folks know what you're looking for. Yeah. Sorry.
Yeah.
Go ahead.
Yeah, I was just gonna say, yeah, I'm guessing you learn, if I click 2 pixels next to each other, and one's red, one's green, and they're different by this much, that's where I'm gonna start seeing the issue.
Correct. Yes. And that's, it all comes down to, practicing it and doing it more. They run us through like simulations of previous events too. And so you can get practice kind of at doing that in real time, in a sense. But yeah, from what I've seen, and even for me personally, we do have certain tools that can help us assess, different things like rotational velocity. But I found more and more that people just kind of do quick assessments on their own, because it's just time consuming to go searching around for these tools and then plotting it where it needs to be and things like that. So yeah, those are really good questions, and I'm glad to share those with you guys.
If minutes count, I am glad that you're not fumbling around on the menu of some program.
And that's really what it boils down to, right? I mean, it's if we're seeing something already, and usually you get so accustomed to it that you can kind of just see stuff. I mean, it's like you can detect signatures a lot quicker. Not saying that we're perfect, and not saying that, even for me, who's only been in here like a year and a half, I still have so much to learn. And I think especially with radar, because like I said, I mean, radar meteorology can be a field of its own. There's so much to learn and know about it.
Humans are really good pattern recognition.
It's a lot of pattern recognition, absolutely. When it comes to radar. And it's not just with storm environments too, but it's also, you think about radar with other things too, like detecting where we might have like mixed precipitation. There's all different types of applications with radar, not just severe weather, but severe weather is kind of where we kind of use it like most heavily, especially with velocity. So one of the things that we do, of course, is with observations, we rely on storm spotters who rely real-time severe weather reports to us. So we rely on, not just the radar products, but ground truth. And that's really what spotters can help provide for us. And for any of you that might have any interest in storm spotters or in being a storm spotter, if you're not already one, stay tuned to our website. We'll actually have, if you go to weather.gov/ILN, that's India Lima November. That's Wilmington's sort of like tag, those 3 letters. We'll have more information coming up here pretty soon, but we usually start doing these storm spotter talks in February, maybe like late February, and those can go through April. And we do a handful of them. Most of them will probably be virtually again this year, if not all of them. But those could be, if you guys have any interest, we talk a little bit more about some of the things, storm structures and things of that nature too, if you have more interest in that. And then I think we'll also, sounds like you guys really know your stuff. I think we're going to plan on having an advanced storm spotter class as well. That'll probably be a little bit later on. But if any of you ever have any questions, Sue, Gary, I know you guys have my email. If you ever have any questions on that, you can, never hesitate to reach out to me and I can try to provide more information. But that one is very long. I think that one is like as long as 4 to 5 hours in length. Likely going to be done virtually, but that we cover a lot of different sections and in a lot more detail for those that have, more of a genuine interest in meteorology, but also could use a little bit more technical analysis and details with some of the different storm structures and spotting different. We talk about some of the different radar features as well that we spot and look out for when it comes to like severe weather. So if that interests any of you, definitely stay tuned. And like I said, don't hesitate to reach out to me about that. So this is just kind of I say silly thing, but, severe weather safety, it's always important to have a plan. Having different things such as a disaster kit prepared. We have weather.gov has different information on severe weather safety. So you can always take a look at more information there about things to have. Of course, always having a designated tornado shelter. Knowing where to go, of course, in your house, of course, a basement if you have it, but the most interior room on the lowest floor is where you want to go for a tornado shelter. Of course, when it comes to severe weather, one of the best things you can do is, of course, notifying your friends and family, just making sure that everybody is aware and alert of potential hazardous weather. And then if you're on the road, also knowing location relative to get to like the nearest sturdy structure. And we always say that the best thing to do is have 3 ways to receive crucial warning information. Of course, some of the most common ones are just getting alerts through your phones, through TV or no weather radio, but always having, several ways of getting that crucial warning information. So I thought I'd throw this slide on here because it's interesting to me, but people have sort of myths about tornadoes. So I threw on 4 different myths here that are kind of busted, I guess, so to speak. But some people believe that tornadoes can't cross bodies of water, which is not true because that happened back in 2012. We had an EF3 tornado cross the Ohio River and unfortunately demolished several dwellings there just past the river. Tornadoes don't hit big cities. Of course, we know that's not true. Here's a tornado located down near downtown Metro. There's been other major cities, Oklahoma City out in the Central Plains, that have been hit from larger tornadoes as well. Myth 3, tornadoes don't hit the same areas twice. Well, we definitely know that to not be true. Xenia is a great example of that, where they've had 2 significant tornadoes roll through that town in both 1974 and in the year 2000. And tornadoes don't occur in the winter is another myth. Well, we had a tornado damage. This is a picture back in 2014. But as many of you are also aware, we had a pretty historic, not in our area, but just south of us throughout Kentucky, we had a really historic tornado in December of 2021. So just this last year. So on December 10th, 2021, these are just some photos here of the long track tornado that you guys are probably aware of. One of the areas that it was most detrimental to was Mayfield, Kentucky, where it just really demolished the better portion of that town. So not only did we have, and I guess this is technically meteorological winter that occurred, not astronomical winter. So meteorological winter starts December 1st. Astronomical winter is a little bit later in December. But still, this is, just one great example that we had this last year, where tornadoes can really occur at any time of the year.
Does that width of 1 mile, is that contact with the ground rotating vortex a mile wide?
That is correct.
Wow.
Yeah. Yeah, so that was observed. And so what you see on the top left here is, so there's kind of 2 major tracks here. So the one on top is the one that did go through Mayfield, Kentucky, and that was the most significant of all the tornadoes. And that's the one where it was long track. So it was it tracked 165 miles, nearly 166 miles altogether. And I think, if I remember correctly, and I think this is on NWS Paducah, Kentucky's website. They have a little bit more information if you're interested on that tornado or the tornadoes that occurred that day. But I think it was on the ground for as long as 140, about 140 miles, which is just, that's just absolutely incredible. I mean, to have a tornado, even on the ground for several miles, is a pretty incredible feat. Something like this, like I said, it's absolutely historic. And it it's one of those things where it just puts into perspective of like what Mother Nature can do. So this is, one of the crazy things is that the one of the meteorologists in these weather offices, when he was typing up the warning for Mayfield, he said this in an interview, is that he struggled to type as he was putting in, because he was basically saying that this is particularly dangerous situation. So they put in that PDS tag, essentially saying that catastrophic damage is occurring. He said that as he was typing it up, he forgot how to spell Mayfield briefly there. And he said it was like his fingers were trembling as he was trying to type up the warning. Of course, at that point there was already the warning out, but this was kind of I think the upgrade sort of version of it. And that was able to be done when you see these images on the top right here. So you see that velocity image. So there's storm relative motion and then a velocity image. And essentially what that is showing, so this is, one of those really good couplets as well. I remember looking at it live too. And at one point I remember measuring what the rotational velocity would have been. And I think I saw it almost as high as about 100 knots of rotational velocity, which I had mentioned before, usually about 20 to 25 knots is you want to put a tornado warning out, and close to 50 knots is the considerable tornado. So that just kind of puts it into perspective of how significant, this tornado was specifically. And it was given, like I said, an EF4 rating. On the track here, the red lines are essentially indicating where EF4 damage was being observed. So just an incredible tornado that occurred last month. And I just wanted to share this with you guys because, I could kind of throw in and talk about it a little bit, but it just goes to show that, not only tornadoes happen at any point throughout the year, but significant and catastrophic tornadoes can occur at any point in the year.
What's the lower line? What was the lower line? Out of curiosity.
Oh, yeah, sorry. I don't think I mentioned that. That was another long track tornado that occurred through the area, but that was rated an EF3. So this is just kind of pulling off of their damage track surveys that they did. So after completing all their surveys, they do this. So all of the little points here are damage points. And so between those points, they're kind of able to rate what the track or what the intensity of the tornado was throughout that. So the top one was this historic EF4 tornado, but there was still another significant EF3 tornado that occurred at this southern line here.
Wow.
Yeah. So definitely a significant day in the weather world. But yeah, I thought I'd just share that with you guys. Now, with the time I have left here, I want to talk a little bit about numerical weather prediction. So this is the side of meteorology where we do our forecasting and use these computer models to try and paint the picture of what we're expecting the forecast to look like throughout basically the next 7 days, which is where we focus most of our attention. So again, we're using all these observations that I talked about previously, surface observations, satellite data, balloons, radar. And we take all of that data and we basically are using these NOAA supercomputers and ingesting all of these observations. And these computers are running all of these different calculations, calculations that are based on what we know in physics and thermodynamics and all these basically different laws of nature. So we take all these observations, it runs the calculations. These supercomputers can make 8 quadrillion calculations per second. They're, like I said, ingesting billions essentially of data points from all these different observations, and eventually are able to provide us with weather information. So this is a sort of complicated graphic here, but I just thought I'd show it because it just kind of illustrates the number of variables that go into a weather forecast. So with these weather models, you can think of them as like they're running all of these different variables and calculating them in a grid space. And so you have to create these grids because otherwise the models would just like take way too long to run. So in a way, these models are simple, like we are simplifying things a little bit for these models, right? We're not able to diagnose, we're not able to measure every single atmospheric particle and assess that. We have to simplify some things, which is why, again, all weather models aren't really going to be perfect. And that relies on our interpretation to try and make the most out of the information that we're getting. But essentially we're taking, so all of these variables at the surface, temperature, humidity, pressure, and then we look at other things too, like heat fluxes, radiation fluxes. And so we're running those calculations through the model, and we're doing sort of horizontal exchanges between these different grid spaces. But within these grids as well, we have ways of measuring vertical exchanges between different levels as well. Because as I mentioned, these models are not just giving these parameters at the surface, but they're also able to tell us different things in different layers of the atmosphere, such as temperature, moisture, and wind, how those parameters are changing as well with height. And so we can do that by examining different vertical exchanges between different atmospheric variables as well. And this also accounts for different things such as like aerosols and precipitation and different things of that nature, clouds too, radiation, and how that impacts heat exchange and energy throughout the atmosphere. So using in this case, the grid spacing is, usually about 10 to 20 kilometers, but if you're using a 10-kilometer spatial resolution globally, or about 5 million grid points. So you take about 100 vertical levels. So again, those vertical levels that are within each grid spacing, and 10 physical prognostic variables. So we're just kind of simplifying it here, taking 10 variables such as temperature, humidity, wind, and you're putting those all into the equations. It produces a model with a dimension of 5 billion. So it's 5 million grid points multiplied by 100 vertical levels, multiplied by 10 variables. So 5 billion calculations for each hour of a weather model are being done. And most of these weather models go out at least 240 hours. So if you have a weather model like this, 500 billion calculations multiplied by 24 hours, that means over 100 or over 1 trillion calculations are needed just for one model run. So just number crunching like this, I just thought it was really unique because it just really shows the amount of work that these supercomputers are doing. So it's just incredible the amount of calculations that they are able to do.
How long does it take to do that trillion calculations?
Yeah.
How long does it take to do a run?
Yeah. So it depends on the model, of course, because you have some models that are more higher resolution and shorter term. So they kind of maybe just go out over the next day or 2 to 3 days. And some models will go out for 7 to 14 days. So the models that it only takes some of the short range models, let's say, so if it starts running at about 7 p.m., usually by about 9 to 9:30 p.m., those shorter range models will be done. So about 2.5 hours. And not only are all the calculations done, but then it's painted essentially on a grid for you to analyze and interpret. The longer range ones can usually take as long as 3.5 to 5 hours to run, because again, you're doing a lot of similar calculations, but instead of just doing it for a few days, you're doing it out to like 10 to 14 days. So kind of depends on the model, but you know, for what you're getting out of it, 4 hours isn't really that bad when you consider all of the factors that go into it. So, you know, ultimately the atmosphere, you know, again, it behaves like a fluid. So a lot of the calculations or equations that we're using in these models are widely accepted physical equations of fluid motion and fluid dynamics. So that's why when you go to school for meteorology, you end up having to take a lot of physics courses and mathematics courses, because a lot of at least what computer models do is the focus on these equations and these laws of physics that we essentially have to follow. So I thought I'd just throw 2 equations on here to scare you guys. The omega equation and the vorticity equation are both shown here. So the omega equation is one way that we're just kind of assessing vertical motion. So this is the way that we're kind of looking at the tendency of an air parcel to essentially move up or down in the atmosphere. And then vorticity is looking essentially at the amount of spin or potential spin that an air parcel might have as it's moving through the atmosphere. So
quick question on the modeling. So you're doing 100 different altitude levels, and so presumably you are getting topography in that.
Yes.
So, so what it's doing is it's treating the atmosphere as a fluid over a rough surface, a defined rough surface, and it's just doing the fluid calculations to see how the fluid would move over around all of that.
Yes, that is absolutely correct. And the higher resolution model you have, the better terrain and topography that'll be ingested into that. But yes, it does take into account like hilly and mountainous terrain.
Gotcha.
I noticed that you said on a previous slide, you said aerosol. Does this involve real-time monitoring of what the albedo really is? Because, you know, there are non-meteorological inputs to that, like forest fires and things like that.
Yeah, and I think that is those aerosols and different things that we get are basically from satellite data.
Okay.
So the satellite data is measuring aerosols and other sort of I guess gases too, like that, anything that can essentially influence changing weather pattern, that's taken into account for. And generally, I think that would be something that we would get from satellite data, those observations. Yeah.
So in the satellite data, you probably have real-time inputs for almost all these grids, but you know, I don't imagine you have a wind speed as a function of altitude, you know, for a spot over the Pacific going up so high. Is that mostly calculational?
As far as I know, yes, that would be mostly
Okay.
calculational. Yeah.
I think it would have
Okay.
to be. And then also, I was also just still thinking about the boundary layer, particularly the bottom. I'm guessing oceans are the boundary condition of a water body is somehow treated differently than a landmass.
Well, I don't know that it's actually treated necessarily any differently.
There's got to be more, you know, moisture pickup over an ocean than over the Sahara, obviously. So I just, do you know if it includes that kind of boundary condition input?
Well, yeah, and I think just with the combination of both ground truth, because we have like buoys that we're getting information from that measure water temperature and different things of that nature too. So we're taking in, and again, there's a lot more like observations and stuff that I have listed here that we're taking in, but we do have some ground truth in a way with like the variables that we're measuring like over the ocean. But I think generally we probably rely a little bit more on satellite information when it comes to gathering data over an ocean, because yeah, you're not going to have weather like 900 weather stations scattered across the Pacific Ocean. like
Right.
we
I
do
guess,
with-
I guess, I mean, I take your point about having ground truth out there and buoys where you actually have real data. But I'm also just thinking about the modeling, and I guess what's coming to mind is humidity. The modeling of a fluid air mass traveling over an ocean as the boundary layer. You know, the bottom boundary is water versus the bottom boundary is land. I would think you could make mathematical assumptions about how that boundary level is contributing to the properties of the air. And so that led me to wonder whether you actually include that in the modeling or not.
Yeah,
I'd be
and
surprised. I just have a quick question about this. It's kind of interesting, Tom Hagedorn here. I'd be surprised if we're not taking measurements of the, like Lake Erie and its effect on our, the lake effect snow and, well, all the lakes, all the Great Lakes and how they affect local weather and the
Yes.
temperature of the lakes.
so yes, we do. Yeah, there is information that's incorporated with that. And we get that a lot more in our higher resolution models where we can have, we get some indications of lake effect, but, there's always, and luckily we don't deal with that too much where we're forecasting, but like Cleveland, NWS Cleveland, they have a lot more that they have to do with that. So absolutely, there's ways that we have of incorporating the potential for lake effect. But even so, usually the models are still way underdoing the potential that we can get, potential snow accumulations you can get for lake effect, because it's when you can get rates of 6 to 10 inches per hour, most models just aren't going to pick up on things like that. But there are ways to kind of account for and not just like what the model is showing in potential snow accumulations, but also just things about like, well, based on the wind orientation, how far is it traveling across the water? Okay, well then based on that, we have a long enough, what's called a fetch, where the wind is traveling over water long enough to pick up that moisture. And then when it's traveling on land, you get some of that convergence because, when it's traveling over water, there's less friction. And as that air converges onto the land, then you get sort of this localized upward motion. And then from there, you can kind of look at, well, what's the temperature difference from the surface to about like the 850 millibar level is usually what we use. And so if you have a big enough temperature difference, then you know that there's a fair amount of instability. And so from that, you can kind of sort of diagnose and say, okay, we're going to have lake effect. How much, or depending on how much instability is in the atmosphere, you might want to, really up those totals from what the models are giving you, just based on, different parameters that we're kind of looking at in assessing the, like I said, the amount of energy or instability that's available in the atmosphere. Because the greater temperature difference you have from the surface to 850 millibars, essentially the more unstable the atmosphere is going to be. Because as its air parcels rise from the surface, they're pretty much essentially going to be able to freely rise in an environment where your ambient environmental temperature is cooling rapidly. So that water or those air parcels, the water vapor, will be able to easily rise and condense. And just have more energy associated with it. So yeah, that's definitely something that's taken into account. As for the coastal and like the ocean regions that we were kind of talking about earlier, so there are models that actually have at least like coastlines and stuff painted over it. So like they kind of know, okay, this is the area where a coastline is occurring. So because of that, there's slightly different, I guess, calculations. There's something that might be used for that. So in that way, I bet they do have a slightly different way of, calculating or doing the calculations essentially in those grid boxes over the ocean versus over land to account for some different things as well. And those are going to be more in our like global models. But there are things that are taken into account, like I said, for coastlines. So I bet that they would have ways of accounting for, doing those same calculations, maybe a slightly different way over the ocean.
And the other boundary, I guess they absolutely must be paying attention to is solar energy.
Yes, and that's definitely something that's also taken into account for as well. Yep.
Yeah, I wanted to ask, Steve brought it up. By the way, I don't want to be stepping on anybody. Should we be using the raising the hands function? Sue?
I think we've been okay so far.
Yeah, why don't we let him finish up if there was
Okay.
anything else he wanted to say, because we're already over time.
Yeah.
And,
So we are.
yeah,
I had two questions I haven't been able to get in.
Now's your chance.
Could you finish up
Yeah,
and
go ahead.
then I'll have my two
Okay.
questions?
Let's finish up.
Okay, we can do that. Yeah, so I won't try to spend too much time here, but so yeah, I was talking about, you know, all the different calculations that go into creating the weather model. So once all the number crunching is done, we get this nice pretty picture that's painted for us. But then comes the part, well, is the solution correct? And for us, our job is basically to determine in what ways is it right, in what ways is it wrong. So for us to look at sort of the realm of possibilities within a weather pattern, of course, we have to use many different types of weather models and compare the solutions. So, you know, differences in these computer models can be attributed to, there's a lot of different factors, but I just picked a few here. So of course, the horizontal and vertical grid spacing, of course, the finer resolution that you use, you know, maybe the more accurate it'll be, but you know, when you get that finer resolution, it's going to take more time to do all the calculations and stuff. So you got to kind of find this balancing act. So that's why usually those higher resolution models maybe only will go out 1 to 3 days because you're getting maybe better data for the near term and representing more smaller scale processes. But you don't want to be doing that, like I said, out through 14 days because there's a lot that can change really in that later time period as well, but it's going to take significantly longer to run all those calculations. Different things too that can affect it: temporal domain, spatial domain, different equations of motion, and then the methodology for ingesting these observations. So again, here's just a handful of different weather models we use. Some of the common ones are the global forecast system, the North American mesoscale model, the European model, Canadian, Japan, advanced WRF, non-hydrostatic mesoscale model, and high resolution rapid refresh model. So these are some of the more common ones, still more that are out there, but again, there's a lot of different data that we can look at and analyze. And it's good, it's both good and bad, right? I mean, because sometimes it's information overload and you can really bog yourself down by looking at a lot of different data. But it can be helpful, like I said, to look at these different models because they run in slightly different ways. Now, the other thing that we do, instead of just looking at different models, is we look at ensembles. So model ensembles are different runs of the exact same model where the initial conditions or equation are varied just slightly from the parent model. So for example, here we have like the GFS model, where we might run it, let's say 50 different times, right? So we're going to get 50 different ensemble members, as well as the original deterministic model, the GFS itself. And when you run it 50 different times with a slightly different change in maybe the initial conditions, so maybe a slightly different change, a perturbation in like the ambient air temperature to start. Just doing these subtle changes, you can see when we're looking at this plot right here. This is a graph of it's quantitative precipitation forecast, or QPF, basically looking at the amount of rainfall potential at the Cincinnati airport. And so you can see that, well, okay, maybe over the first like few days, there's good agreement, there's no precipitation. We start to get precipitation, then you can see sort of this like spaghetti plot where you see all these different lines. So of course, you know, in the shorter term forecast, like up through day 3, the range is a little bit smaller, but we're still looking at a pretty significant range here from about 0.2 of an inch to 0.9 of an inch, right? And that's you're running 50 different ensemble members. They're all giving you different solutions, but you might be able to come to a little bit of a consensus there. Well, what happens when you get to day 5? Well, now the range goes from about 0.2 of an inch to 1.9 inches of rain. And that just goes to show that, with these models, it's very difficult to really narrow down a forecast when you get in sort of that 5 to 7 day range, and then even further down the road. And that's really why at the Weather Service, we really just focus on the first 7 days. Outside of that, predictability just becomes way too low because there's just so many different factors that can go into, changing the potential environment that we're expecting. That it's just so low confidence that we really don't want to put that information out. And so this just goes to show, again, how significant that range can look like when we're running these different ensembles. But ensembles are crucial because we can look for different things where we can look for agreement, right? We can look for these clustering of ensemble members. So like this black line here, I believe is showing the ensemble mean. So we can kind of look at, okay, well, here's where the average lies, but look at this clustering here, right, in this area. So, generally speaking, over the 5-day period, we might say, well, our range is 0.2 to 1.9 inches, but our highest confidence is probably going to be in this like 1 inch to maybe 1.2 to 1.3 inch range, because this is where a lot of agreement is shown in ensemble members. So that's why it's really important to have this shift towards like this ensemble approach where we're looking at, many different runs of the same model, because then we can kind of find and narrow down on this area where there's a lot more agreement in these models. And like I said, as you go further out, there's less and less agreement, but it's still very helpful for us to diagnose and try to find a more appropriate answer in these model solutions. So this is basically like my last slide here. But, I like to throw on this slide because it shows why the Ohio Valley and really even why the central and eastern part of the US is one of the more interesting locations when it comes to extreme and active weather. So it all really boils down to location, why we have some of the most extreme weather in the Ohio Valley and why it's so challenging. We get all different types of weather, right? We know that we get severe weather in Ohio. We get all 4 seasons. We get winter weather, and we can get those, like I said, severe weather at any time of the year. And it really just has to do with all the different air masses and topography that's around us in the United States that ultimately puts us in a situation where we can get a clash of basically all these different air masses. So you have all these different unique features geographically across the United States, right? So you got the Rocky Mountains, you got the Pacific Northwest. To our north, we got Canada, which is a great source for continental cold air. We got the desert Southwest. We got the Gulf of Mexico. So, of course, since we live in the Northern Hemisphere, generally weather moves from west to east so there's generally lower atmospheric pressure on the poles, higher pressure near the equator, and something called the Coriolis effect. The Coriolis effect is essentially the effect that we get from Earth's rotation, right? So because of Earth's rotation, we get this like Coriolis effect. And so we have a lot of our weather that tends to move from west to east. Well, because of that, so you have air that moves from the Pacific Northwest and it moves over the Rocky Mountains, right? So you're already kind of starting with maybe some saturated air off the Pacific. Well, it moves over the Rocky Mountains and it reaches the eastern side of the Rocky Mountains towards the Great Plains. Well, as this air begins to move down slope, it acts to warm it and dry it out. And then the air moves further eastward and it encounters the desert Southwest, right? So this hot, dry air from the desert. And eventually, as you move even further eastward, it clashes, this hot, dry air, it clashes with the moist air moving north from the Gulf of Mexico. So in this area here, the Northern Plains all the way through like the Midwest region, you get some of the most active weather, right? Because you're having the clash of the continental cold air mass from Canada, the Gulf of moisture or Gulf of Mexico moisture, and then the influence of air moving from the Pacific Northwest and interacting and encountering the Rocky Mountains and the desert Southwest. And so when you get all this hot, humid air, near the surface, that ultimately can create, a more unstable air mass. And so when you have all of these air masses clashing, colliding, and working with each other, you can get some of the most, like I said, extreme and active weather in the world. So that's what really makes the United States, and specifically the central and eastern United States, very unique compared to other parts of the world. So I'll go ahead and end this presentation here, and I can take some more questions as well. Like I said, I don't really have anywhere to be, so if you guys have any more questions, feel free to ask. So I thank you guys for your time so far today. It was a pleasure talking to you all, and maybe we can do this again in the near future. So thank you all.
Yes, thank you.
Thank you.
Thank you, Logan. You did a really good job of the presentation and handling all the questions.
Yes, thanks.
Yeah, absolutely.
Can I get a couple of questions in?
Yes.
Okay, so is it easy to put your hands on those equations you had?
Yeah, let me go back to that. Here?
Yes, without getting into what these mean. My understanding is when you have equations, you have a lot of data you have to put in to solve for one number,
Correct.
right? And the data comes from, your balloons and all of that. And, okay, what is the variable that's left unknown that you want to solve for in these equations? It looks to me like it might be delta squared phi or the partial derivative of it. Which
Yep.
is the important thing you were after when you use these equations?
Well, in these equations, so like what we're solving for in that first one is like you said, it's so this term right here is
Oh, it's the red box?
the whole box is like the term that we're solving for. So
Okay,
this,
you want to know what that box is. Okay,
Correct.
and then the second one?
and then the second one is, and I guess I should have boxed it as well, but it's basically this whole part of the left
Let me
side of the
see.
equation.
So these guys are magic numbers that go into your graphs.
Correct. Yeah. So
Okay,
these are essentially solving. Yeah. So like the term on the left here is the omega term, right? So omega is like the assessment of vertical motion.
I see.
And then on the left side here, down here, it's vorticity. So this whole term right here actually represents,
So that's a definition of vorticity.
what's that?
That is the definition of vorticity, the left side.
Correct. So yeah, and you can see it says quasi-geostrophic vorticity. So quasi-geostrophic means like generally geostrophic winds. So whenever you're calculating this stuff, again, I mentioned that you have to make like some simplifications, right? So geostrophic is essentially implying when you're doing just geostrophic, I think it's implying that there's no like vertical motions with it, but quasi-geostrophic is actually now it's partially geostrophic, but now we're starting to incorporate things such as a vertical motion and spin within the atmosphere. So these are two very common equations that.
So it's multidimensional. It's not just a linear or planar.
That is correct. Yeah.
Okay, I got it. So it's a vector. And for some reason, it has physical meaning and implication about weather behavior. And that came up from, I guess, physicists developing this definition as important.
That is correct. Yeah. So it is a vector. So like the geostrophic wind is essentially the wind that we're measuring that's flowing parallel to
Okay.
height contours.
Okay, good. My second question is high rises and tornadoes. Are they generally safer or more at risk?
High rises,
Yes.
those would be more at risk.
Okay, thank you.
Yeah, and Tom Hagedorn here. I've kind of held my fire. This has been great, Logan. I have two, these are non-technical questions, two sort of non-technical questions, and then one quick point I wanted to make that I found interesting. First one's a real easy one. So I love weather and this sort of thing. But I'm not really like the storm chaser, storm spotter sort of person, but I love talking about these things and studying meteorology and so forth. Is there any local group? I know the American Meteorological Society does have local groups. I do not think they have a local active one. Is there any group of people that have a similar interest to me that you're aware of?
That's a good question. And this is something that our office talked about recently. There used to be like a group from Cincinnati that I don't remember their exact name, but they used to be like a sort of like a organization that was responsible for meeting and talking meteorology. It was kind of, just like nerding out about meteorology. But I think that group no longer exists. Now, so locally in our area, I'm not aware, unfortunately, of any group that meets like routinely and does stuff like this. But what I will say is that I think our new meteorologist in charge, he has an interest in potentially pursuing a group where people can get involved and help us out with. So like it would be a group that is kind of responsible for, like kind of being a sort of like a storm spotter, but like more advanced in the sense that you're kind of in charge of helping running like a social media account. Cause I guess there's a group that does this down in Tallahassee where they do like storm spotter stuff like through social media. But they also report other information as well. And so I guess that's more on the side of like doing storm analysis and stuff. They're not like meeting to talk about weather, at least as much as I know.
Yeah.
But
and I appreciate that. That's kind of my interest. I do appreciate folks that do get involved and try to help with this, but that's great. Yeah, I've looked, I haven't found anything. The quick point I wanted to make, and I don't know if your local person would be interested in this, but I've actually done quite a bit of research on Cleveland Abbey, and he's a pretty amazing person. I'll just give you one quick snippet, and that's it. In 1912, he was awarded the Simon's Medal by Lord Kelvin, which was the highest honor the UK could bestow for achievements in meteorology. And so he was not just one of those founders of science, but he also had to get involved with the government with funding. And he like fought for weather observations and forecasting for like 50 years. Yeah, and it's to me, it's amazing that this guy, and this all started right here in Cincinnati. You can go out Lafayette Circle in Clifton, drive to the end, and it's right there. It's on the circle. It's the first building. You can't miss it. I earned a Bachelor of Science in physical geography in the 60s at UC. And one of our classes took a trip up there, and they still had some of the instrumentation. I don't remember if it seemed to me like it was very old meteorological equipment. But anyway, I'll actually put my phone number up. If anybody's interested, I would love to give a talk on Cleveland Abbey. I've done a lot of research on him. It's a pretty fascinating thing. We need people that will do science, but also there's a promotion and a political aspect as well to get it funded. So my phone number, it's 513-403-0643. And I'll probably contact the observatory too, because they might have an interest as well. But anyway,
Sue, you got that right. I think we got our speaker for March, maybe.
I'll do it. I'll definitely do it if you're interested. Now, this would be more history. It's not going to be.
Yeah, that's fine.
Okay.
Yeah,
that's fine.
It would be more history, but he was an amazing person.
Did you get the phone number, Sue?
No.
Let me repeat it. It's
Okay.
So it's Tom Hagedorn,
Mhm.
513-403-0643.
Okay.
And
I
gosh,
can also-
Tom, I'm sorry. I just realized we recorded that and I had a question about sharing the
Oh,
recording.
That's okay. It's okay. I don't, I mean, I don't think this is a controversial.
Okay, well, it's
I
just your
don't think it's
personal information.
controversial, so I'm willing to take the risk. That's okay.
So,
Okay,
but
what-
briefly,
Why don't you
Sue,
stop the recording then now?
You should give
yeah,
us the.
I'm gonna go ahead and do
You
that.
should give us the email also.